You know that little block that charges your phone? We plug it in every day and just don't think about it. But have you ever actually wondered what's going on inside? Because it's performing a tiny, incredible miracle of physics every single time. So let's do it. Let's dive in and unpack the science inside your power adapter.
So here's the big question for this whole explainer. What is actually happening in there? How does this little plastic box take the powerful, kind of wild electricity from your wall and turn it into the precise, gentle power your smartphone needs to charge up without, frying itself?
Well, the first problem is that the power coming out of your wall socket is just the wrong kind of power. Wall sockets give us alternating current, AC, where the electricity is constantly flipping its direction, back and forth, back and forth. But our phones and pretty much all our electronics, they need direct current, DC, which is a nice, steady one-way flow. So the adapter's #1 job is to make that conversion happen.
To really get how it does that, we've got to zoom way, way in. We need to talk about the fundamental particle of electricity itself, the electron. Seriously, everything that happens from here on out is just about finding clever ways to control the flow of these tiny little particles.
So one of the earliest ways we figured out how to control electrons was a process called thermionic emission. It's a fancy term, but it's basically just boiling electrons off a super hot piece of metal. Now, this isn't what's happening in your tiny charger, but it was a huge first step in learning how to get electrons to do what we want. And once those electrons were free, we could start steering them. By heating up a filament and then using a strong positive voltage to attract them, early scientists could literally pull those escaped electrons into a focused high-speed beam. And that beam was called a cathode ray. And these cathode rays had really predictable properties, right? They were negatively charged, they flew in perfectly straight lines, and they carried energy. Mastering this was a huge deal, but for modern electronics, we were going to need a much better, much smaller way to do things.
Yeah, that whole heating filaments in a vacuum thing, super inefficient and bulky, definitely not going to fit in your pocket. Modern electronics needed a solid-state solution, and that solution starts right here, with the first key component for solving our AC to DC problem, the semiconductor diode.
A diode is, for all intents and purposes, a one-way street for electricity. Think of it like a valve. Current can flow through it one way, no problem. But if it tries to turn around and flow back the other way, nope, the gate slams shut. And this one-way property is exactly what we need to tame that alternating current.
So how does it do that? Well, the magic is all in its internal structure. When current flows the right way, what we call forward biased, a tiny internal barrier shrinks down, letting the electricity pass right through. But if the current tries to reverse, that barrier instantly gets wider, blocking the flow completely. It's ingenious.
And this whole process, this trick of using diodes to turn that back and forth AC into one-way DC, well, it has a name. It's called rectification. This is it. This is the heart of the solution to the problem we started with. We're forcing that chaotic electricity to finally pick a lane and stick to it.
Now, you can do this in a couple of ways. With just one diode, you get what's called half-wave rectification. It just chops off the negative half of the AC wave, which works, but it's super choppy. But with a clever setup of 4 diodes, called a bridge rectifier, you can actually flip the negative half so it becomes positive. This gives you full-wave rectification, which is much better, a continuous but still kind of bumpy stream of DC.
And that brings us to the next problem. So this full-wave power is way better, but it's still rising and falling, rising and falling. It's like driving on a really bumpy road. Your phone's processor, though, it needs a perfectly smooth highway of power to work right. So is this bumpy DC actually good enough? The answer is nope, not even close. To smooth out those bumps, we need one more little component, a capacitor. The best way to think of a capacitor is like a tiny, super fast battery. It charges up when the voltage is at its peak, and then when the voltage starts to dip, it instantly discharges, filling in the gaps. And the result is a much smoother, much more stable DC voltage. Okay, so we've solved the basic power problem. We've converted that wild AC into smooth, usable DC. But modern electronics are about more than just power. They're about control. They're about information. And that brings us to what is, arguably, the most important invention of the 20th century, the transistor. So what is this thing? Well, it's a tiny little component, usually with 3 legs, and it can do 2, frankly, magical things. It can act as an amplifier, making a small signal much bigger, and it can act as a lightning-fast switch with 0 moving parts. And the secret to both of those things is that a tiny little trickle of current at one terminal, the base, can control a huge flow of current through the other two.
And this is the whole secret sauce. This principle of amplification is everything. It means a tiny electrical pulse can act as a trigger, switching a much bigger current on or off in an instant. And that, right there, is the fundamental basis of all digital logic, zeros and ones. Okay, let's bring this back to the real world. Ever wonder how an automatic streetlight knows exactly when it's dark enough to turn on? Well, the answer is a beautifully simple little circuit that's controlled by a transistor.
The logic here is just its genius. The circuit uses something called a light-dependent resistor, which, as the name implies, changes its resistance based on light. When it gets dark, its resistance goes way up. That allows a tiny current to flow to the transistor's base, which acts like a key turning at a lock. It unlocks the transistor, allowing the big current needed for the streetlight to flow through and turn on the lamp. It's a completely automatic switch.
All right, let's pull back and look at the big picture here. We've gone on a journey from the fundamental electron to diodes that act like one-way streets, to transistors that act like tiny switches. We started this whole thing by looking inside a simple power adapter. But as you can see, these exact same components are the building blocks of our entire digital world.
So let's just recap that journey. We learned how to control electrons, these little messengers of electricity. We used diodes as one-way gates to turn AC into DC. And then we saw how transistors can act as tiny, automatic switches in amplifiers, which is what makes all computation possible. Every single piece of modern tech is built on these foundational ideas. So what does all this look like in the tech we actually use today? Well, here's a number for you, 15 billion. That is a pretty conservative estimate for the number of transistors that are packed onto a single advanced smartphone chip today. 15 billion, tiny little switches.
And every single one of those billions of transistors is a direct descendant of that simple switch principle we just talked about with the streetlight. They're all working together, flipping on and off billions of times every single second to make everything on your screen happen. It all started with figuring out how to control a tiny particle, and now it's all right there, in the palm of your hand.